No. So nice to be here. I'm glad at last the physics is in a reasonably good surroundings here, and with the building and so on, and this institute, and also nice to be in the ICTS meeting. I'm especially happy that this meeting is dedicated to Ramakrishnan, whom I have known from for a very long time. I think when he started his independent professional career in the old institute in IIT Kanpur, that's where I was the head of the chemistry department there, or dean or whatever I was. And when young Ramakrishnan came at the time, I've known him since then. Occasionally we have even collaborated. I've written a few papers together and even a little book. So I think it's a wonderful thing to see, not to see people getting old, I don't mean that. It's wonderful that you are arranging something in his honor. By the way, I find really exclusively a meeting of theoretical physicists. I see one or two sprinkling of experimentalists, but of which I'm not even an experimental physicist, I'm actually a chemist. But even though I'm a chemist, I dabble a bit in physics. I publish in physics journals. My degree is in chemical physics, actually, my PhD, so it doesn't matter. I guess I hope you will put up with the kind of talk I give and the way I talk. I talk differently, but the language will be slightly different from those of physicists. But today I thought I would talk on multiferroics. In fact, I had planned to talk on carbons, actually. I do a lot of work on graphene and nanotubes. I had some very interesting new results in the last that we have found in the last few months, but I changed the topic because in the last few weeks we have had lots of results in multiferroics. I would like to present to you some new things in this area. Is this working? It is working, okay. But you all know multiferroics are supposed to be materials which are ferromagnetic and at the same time ferroelectric, possibly even ferroelastic. And we know what ferromagnetic materials are and what ferroelectric materials are. But it's very difficult to get them together because the multiferroics are those where you want to have a magnetic material, that means you need d electrons generally, and ferroelectrics are those where you do not want d electrons, and how to get them both together, both properties together in the same material, were difficult. So many people wrote articles even 10 years ago or so, why multiferroics are going to be very rare. In fact, why are they so rare? Because of this difficulty of finding magnetic and ferroelectric properties in the same material. Of course, worse than multiferroics are these magnetoelectrics, where the electrical and magnetic order parameters here, the magnetoelectrics, are even fewer, and where you apply an electric field, you get magnetization, or apply a magnetic field, you get polarization, electric polarization, and so on. So magnetoelectrics are very, very few, and I'm going to talk make a few observations on these materials today. Just for the, again, people reminding you, some of the important properties of ferroelectrics, you know, are the symmetry, they have to be insulators generally, you need a D0 system, the size of the ion has to be small, particularly in barium tight-made type of ferroelectrics, and so on. And then in ferromagnetism, of course, everything is opposite. You need the magnetic and d electrons, and so on. You know that this is not necessary for a meeting of this kind. Now, what happened was about 10 to 11 years ago, there was a sudden burst of activity in the area of multiferroics. At that time, there was an article which has been highly cited, which says, why is it that there are very few multiferroics? That is the title of the article. And in spite of such limitations I mentioned, there are a number of ways we can design multiferroics. People have found ferroelectricity in materials with a magnet ion due to a number of possibilities. The tilting of polyhedra is one of the earliest ways people got ferroelectricity in a material like MnO3. For those who may remember, who may not remember, I'll just refer to that famous paper, a number of papers, a Fleming, many years ago, where we find that ferroelectricity is driven by the electrostatic and size effects are buckling away manganese-oxygen polyhedra in this particular case. This material is an antiferromagnet with a near temperature of very low temperature, around 80 Kelvin, but ferroelectric at a very transition at a very high temperature. This is a typical material where the polyhedral tilting gives rise to ferroelectricity. And now you can see what happens in this. To get used to the experimental things that we do, if you see at the magnetic transition, many of such materials show a dielectric anomaly. That is one of the ways people identify materials of this kind as being probably multiferroic, where you find a dielectric anomaly in the magnetic around the magnetic transition. That is a typical thing one finds in these materials. Well, similarly, lutetium manganite is also similar material where polyhedral tilting gives rise to the ferroelectricity. Look at that. That is the near temperature around which you see the dielectric anomaly in this material. These are very well-known materials, the LuMnO3 or YMnO3, and there are other materials where magnetic ordering, spiral magnetic ordering of frustrated magnetism gives rise to ferroelectricity. I'm quickly going through this because I'm not going to talk about my work in this area, but some of the new things. PBMnO3 is a very well-known solid. There are lots of papers in this in the last 4 or 5 years maybe. It is an orthonormically distorted perovskite, well-known perovskite, and this is a spiral magnetism, and you can see because of this kind of magnetism, you get very, very interesting profiles of magnetization and dielectric anomalies, and you find dielectric anomalies around the magnetic transition, and magnetic field induces changes in the dielectric constant. That is the main thing. And magnetic field induced changes in dielectric constant is very beautifully seen in some of the data that I've just shown you here in PBMnO3. A third system I'll just quickly mention is frustrated magnetism, again in manganese oxides, with very well-known system RMN205, where R is a rare earth. This is a magnetic and ferroelectric transitions here. You see the near temperature here and the ferroelectric transition. Here the phase diagram has been worked out. A lot of work has been done on materials of this kind as well. And here you can see the temperature dependence of the magnetic susceptibility here, and then we also show what happens to the dielectric constant. You again find very nice dielectric anomalies around the magnetic transition and the heat capacity anomalies. A number of these studies have been done, well, over the years, particularly in the last decade or so. Now today, again, I have some more data to show how there is polarization reversal by magnetic fields and polarization flipping by applying magnetic field in materials of this kind. Now today I'm going to talk about the last 3 materials and one or 2 new ones that I've added to this list. One of the first things I'll talk about is the so-called lone pair effect. You see, in a material like bismuth manganite or bismuth iron compound, bismuth ferrite, bismuth has a 2s6s lone pair. That lone pair gives rise to ferroelectricity in this material. This was predicted some time ago, and one of the more well-known examples even that have been there for a very long time is bismuth ferrite. It is very well known because it's been known for I don't know how many years, at least 8-10 years, where this material is ferroelectric at very high temperature and antiferromagnetic around 600 K. This material has been used even technologically in some applications, and this is a typical material where 6s lone pair seems to play a very important role. And you can see here the magnetoelectric effect. I don't know whether it is working. Yeah. Magnetoelectric effect in these materials, and you can see polarization here, and then you also see magnetization here showing of this material and magnetoelectric effect in the inset. So this was known, this has been known. So what happened at that time was there was a paper showing importance of the 6s lone pairs in these bismuth compounds, and those calculations showed that these stereochemically active lone pairs would be a driving force to give rise to distorted low temperature structures or ferroelectric structures. And then this predicted, therefore, a material like BIMnO3, where bismuth lone pair would give rise to ferroelectricity, would be a very interesting material. What happened also around the same time was we had found out, and also some others, that bismuth magnet was a ferromagnet. You see, till now all the materials are shown were antiferromagnets. So the first ferromagnet we knew, so this was around 6-7 years ago. Well, we thought, well, if this is true, is there going to be ferroelectricity in BAMNO3? So the first few pieces of work we did in Bangalore showed, well, this is the ferromagnetic transition. We did find, well, the hysteresis loop is not very good because it's a decay material, but we did find polarization of some sort, weak polarization in this material, electric polarization, and we said it was in fact a ferroelectric. And we even showed how orbital ordering gives rise to ferromagnetism in these cases. We published some paper. So very soon after we did this, Kimura, this Takura also showed that this material, in fact, is multiferroic. And the ferromagnetic transition is around 450 Kelvin, and ferroelectric, we said, is around 100 Kelvin. Well, therefore, this is the only ferromagnetic ferroelectric material. Only then, even today it is. So we thought it was very nice, but right away there was a lot of criticism of that, saying this cannot be true because a lot of theory was done, and all the theory predicted this space group of this material to be a centrosymmetric C2-C. Well, then how can you have this ferroelectricity? And also the polarization value we found was very low. And is it ferroelectric? Or is it all due to impurities? In fact, all this material, but these experiments are very difficult in some materials of this kind. I hope you all know that, because you cannot make bismuth manganate ordinarily. You have to make it at very high pressures. Whenever you do high pressure synthesis of oxides, you always get 5 to 10%, 3% impurity. It is impossible to make it 100% pure because it is not under your control how you are making it. You put all these materials in some kind of an oven and at very high pressures, and somehow you end up with some impurity. So that was another problem. In fact, Takura in his paper in PRL said, oh, Professor Rao's sample had a 5-10% impurity. He made a comment. I mean, it is nice to get a paper in who criticize somebody else a little bit. And his sample has 15% impurity. So data I found. But anyway, it doesn't matter. So everyone, he also made the high pressure synthesis. This was the problem. I tell you, typical problem of a material of this kind. Even today, the problem is not complete. So this was the problem until 2-3 years ago. So immediately we said, look, let us re-synthesize this material very carefully. Unfortunately, we can't do this work in India. So we sent students and my colleague, faculty, Sundaresh, Dr. Sundaresh, they go to Japan to make these samples in NIMS and also in the other laboratory in Tsukuba. Well, we could make very, very good samples of bismuth manganate, according to me, where we had complete control of the oxygen stoichiometry. You see, the reason this is important is when we put the manganese oxide, bismuth oxide, or carbonate, some carbon dioxide will always react with an oxide, you get some carbonate. All such impurities are avoided. Anyway, we need all that. And we could make different samples, 2.99, 2.89 oxygen, 2.84. And as we made it, we found that the properties depended on this oxygen stoichiometry, and you could get very good ferromagnetism when you were around 2.9 or 2.85. And the ferromagnetism, we didn't find it very close to stoichiometry. So it was, even the dielectric properties varied with oxygen stoichiometry of bismuth manganate. And in fact, we did ferroelectricity. But as soon as we did that, again, another group in Japan did what we call a pair distribution function analysis. I hope again you all know that in work of this kind, X-ray diffraction is absolutely hopeless. Crystallography is a useless technique when you are interested in centrosymmetry, whether it's true or not. The average structures you get from ordinary crystallography has been what is happening? Huh? What is that? Huh? What is that?
No, it went to Stanford.
Why? No, I didn't touch anything.
Nothing like that.
Okay, leave it. Leave it over. Don't overdo it now. Leave it. Whatever it is. Oh, leave it. No, leave it. Don't make a big thing out of it. Okay. they did pair distribution function analysis, but this again, as an experimentalist, I was about to point out, crystallography becomes almost useless because here's an average structure. It's extremely difficult to determine whether something is really centrosymmetric or non-centrosymmetric by simple crystallography. And the pair distribution function is very good usually in such things. And they found actually maybe for some reason, it is in fact non-centrosymmetric. They wrote a paper where they found in the same material grains or domains of two different types, one being centrosymmetric, another being non-centrosymmetric, and so on. That's the paper that came. This is how the work has been in the last few years on a very important material, which is the ferromagnetic ferroelectric. Then you see, just last week, last month or 2 months ago, the class definitely established from Cambridge. Paul Midgley has done a lot of work with us. We're using convergent beam electron diffraction, has definitely shown that this even 2.99 is a non-centrosymmetric crystal with this phase group, and 2.94 is also non-centrosymmetric with CCM1. So this somehow justifies our old work. Probably we were dealing with a ferroelectric, which is actually non-centrosymmetric. This is as of last 2 months. There may be more papers coming saying this is also wrong. I don't know. But as far as I'm concerned now, it looks like, depending on the oxygen stoichiometry, small changes in oxygen stoichiometry, one can have different structures and different space groups. And many of these space groups that we have found in bismuth manganate are in fact non-centrosymmetric, and it looks like it is in fact ferroelectric as originally thought of a few years ago. Now, this is one of the things we have done in some detail. And in another area we have worked on is looked at the ferroelectricity that comes from charge ordering. There have been several papers on charge ordering in iron oxides, like rare earth ferrite. This paper again from Japan and also from Oregon University, where they found the charge ordering in rare earth ferrites gives rise to some magnetoelectric effect and also multiferroic properties and so on. So we have looked at that. Again, we found in a number of these rare earth ferrites, we do get ferroelectric behavior or multiferroic behavior due to charge ordering. And this is true of a number of ferrites. So this brought us to look at the rare earth manganites. Rare earth manganites, as you know, are the materials which show colossal magnetoresistance and charge ordering, orbital ordering, and so on. And also they show a lot of phase separation. And they show this tremendous magnetoresistance, the classic material being the lanthanum, calcium, manganese oxides. But the charge ordered systems are very important here, and these are the well-known charge ordered systems, ND.5 Ca.5 MnO3 or ND.5 Ca.5 MnO3. And these charge ordered system crystallography, everything has been done. We know they are definitely charge ordered, because in the sense that there are two states with different charges. It would not be exactly 3 plus and 4 plus, but definitely there are ordering due to these two different charges. Now, these charge ordered states, of course, can be destroyed or transformed to a metallic state or a ferromagnetic state by a number of ways, by chemical means, by pressure, by electric field, and all this has been known about these manganites for some time. Now, these materials also show ferroelectronic phase separation, where in the same material you have ferromagnetic and antiferromagnetic domains, or antiferromagnetic droplets in ferromagnetic matrix, or ferromagnetic droplets in antiferromagnetic matrix, and so on. These have all been described. Now, at this time there was a paper by Komsky where he said that you can have two types of charge ordering, the so-called bond-centered and site-centered charge ordering, and the bond-centered and site-centered charge ordering, when he has given the typical figures. There are some compositions where you can have ferroelectric state as the ground state. That is the paper that he wrote. And we were at that time looking at possible ferroelectricity in charge-ordered manganites, and what we found at that time was definitely there is some dielectric anomaly and magnetoelectric effect in some of these charge-ordered magnets like MD.5, Ca.5, NO3, which is a very good charge-ordered system, where the electric, you can see the effect of magnetic field is fairly substantial. But this was again not enough. We did many other very much better charge-ordered systems like PR6, Ca.4, NO3, which Combs talked about. We found tremendous effect of magnetic field on the ferrodielectric properties, and also sort of a broad maximum around the charge order and transition temperature in the dielectric properties. Even this may not have convinced people, the magnetic capacitance in a material of this kind. So we did world's best insulator known, 1.5 Ca.3. I hope you all know that when we made this many years ago, Tokura applied nearly 40 Tesla magnetic field, and you cannot destroy the charge ordering. In fact, it is such an insulator, the resistivity doesn't change even at 40 Tesla magnetic field. So we tried that, and even in this material, we do find this maximum in dielectric constant around the charge ordering and the extension, and the effect of magnetic field on the dielectric property. So it looks like as if they are in fact multiferroic. Well, this again the same slight change in composition to distinguish so-called side-centered and bond-centered sort of charge ordering. And we also did some second harmonic generation in these materials, found some second harmonic generation materials of this kind. Well, we also did an experiment in this charge-ordered material to where we take, I hope some of these magnetites, when you apply an electric field to charge-ordered magnet, the charge-ordered state melts and it becomes metallic. And by applying an electric field, there's a very, very nice number of experiments done in Bangalore along with Raichandra here. And in fact, what we did was when you apply an electric field to get a magnetic flux in the material, that measurement also was done to show there is in fact coupling between the electrical and magnetic outer parameters in magnetites of this kind. Okay, this is the whole story in my lab until about a year ago. And I just want to tell you what all I've been doing last about 4, 5, 6 years. And now I'm going to tell you something that we have done in the last few months, particularly last 6 months or so, which has been very, very interesting. We have looked at a very simple material. You see, I hope you all know aluminum oxide is a very well-known material with a corundum structure, R3 bar C space group. Alpha iron oxide is also corundum structure, R3 bar C space group. However, if you put together 1-to-1, you make AlFeO3, but it's no longer R3 bar C. Even now it is a mystery why AlFeO3 is not the same as Al2O3 or Fe2O3. For some reason, it becomes a non-centrosymmetric PNA21 space group. And it's amazing. The stable structure of this material is that PNA21 space group, not R3 bar C. This, of course, actually, if you put pressure on it in a particular way, I can transform this to R3 bar C, but it is not the stable structure. If you warm it again, it goes back to this structure. This was a mystery. We have done a lot of work on these compounds now. What is it? And the gallium ferrite is the same structure, PNA21. We'll re-examine the crystal structure. For example, it has 2 iron sites, Fe1 and Fe2, 2 octahedral sites. The aluminum has tetrahedral sites and also octahedral sites. So this is the kind of crystal structure. The magnetic structure is a collinear ferromagnet. Well, some people have called it canted antiferromagnet. I think the correct description would be collinear ferromagnet. And where Fe1, 2 types of iron sites are ferromagnetically interacting, and 2 other iron sites interact antiferromagnetic. So this was the structure that we determined recently. And then magnetism is like this. You can see aluminum ferrite, very nice. This is the real temperature around 250 K. You can also put gallium in it. As you know, aluminum ferrite, gallium ferrite has the same structure. You can make a whole bunch of compositions in between AlFeO3, JFeO3, all having the same space group. And of course, the real temperature keeps varying with the composition. I'm showing one composition to show they all have similar magnetic properties. And this is what is interesting is this material, like gallium ferrite, I could show for others too. Is it ferroelectric? Well, when we look at it in detail, you see, we don't ever measure ferroelectric hysteresis here, because in leaky materials you get very bad hysteresis loops. But we have done as you can see, pyroelectric current measurements in this gallium ferrite, you see this maxima depending on the pooling field, positive or negative pooling field, you get maximum or minimum corresponding to a transition, ferroelectric transition. And this is the polarization, quite large polarization in gallium ferrite, corresponding to maximum around 103. That is the thing. Not only that, the polarization, where is it? Magnetic field, which over here it is a bit high magnetic field, but still there is magnetoelectric effect in these materials. And not only that, we also find, I hope you know the solid state physics data in the old days from Bell Labs, Ramaica, and a number of people try to do a lot of work on this kind of materials. This was about 50 years ago. So we want to increase the real temperature, and others, we even made compositions of this kind which are the same force group. They also show ferroelectricity, magnetoelectric effect, and so on. This is a very interesting thing. Why such a simple compound which is showing ferroelectricity? Of course, it is magnetic, but as I showed you, it is a ferrimagnet. It is a ferrimagnet and ferroelectric at low temperature. This has been a very interesting. Oh, but this is aluminum ferrite. This is also definitely showing similar behavior as gallium ferrite. Aluminum ferrite, as I assumed, has done a lot of Raman work recently to look at these transitions, look at the spin phonon coupling in these materials. Today I'm not showing all those data. So this is the main thing. Why are simple materials of this kind showing multiferroic and magnetoelectric behavior? They are multiferroic and magnetoelectric. I've shown the AL.5, GA.5 that also shows similar behavior. And this is the magnetodielectric measurement. You see very large magnetocapacitance, as much as 50% if you use the right frequency in some of these materials. And you can see the magnetocapacitance reaches very large value depending on the composition, between 20 and 50%. Very, very large magnetoelectric effect, very reasonably good magnetoelectric effect, and definitely, of course, therefore, very interesting material to look at. Of course, we have also done magnetoresistance, and not bother you. There is no magnetoresistance in the material, not large anyway, because the magnetodielectric effect is not due to magnetoresistance. It is definitely a genuine magneto. It is less than 1% in many cases, 2% maybe in one case, but generally, even in cases when there is very small magnetoresistance, we find large magnetodielectric effect. So what is the origin of ferroelectricity? These are the things we are looking at, and Professor Wagner, who is not here probably, he is a theoretician who is working out some theory and why it is so, and a lot of work has been done. One of the simplest explanation right now for this is there are two magnetically inequivalent Fe3 plus ions. As I told you, two different types of magnetic interactions. One is ferromagnetic and there is antiferromagnetic interaction in between the two octahedral sides of iron. And that probably, and that in addition to the disorder that is there, which I didn't talk about in the beginning, is responsible. So basically it is breaking of inversion symmetry. Breaking of inversion symmetry is the one that is causing this ferroelectricity according to us. And this work is not yet published. It is just what has come out of the lab. We are just about to write up materials of this kind. So this is one thing that has come out of our lab in the last few months. Now, another thing that has been done by, along with Professor Sundaresan, who has done much of the work, is look at that. This is a very interesting material. Why FeO3 is a well-known orthoferrite. I hope you know these are all the bubble domain materials. For those who are young, I hope you know what bubble domain materials are. Very well-known magnetic materials. In the, say, 30, 40 years ago, they made big news, these bubble domain materials. It belongs to that family, orthoferrite, antiferromagnetic at high temperature. This, I told you, is a multiferroic material. Now, with a very high Curie temperature for ferroelectricity, we can put these two together. A number of compounds can be made of YFE-MnO3 with Fe.8, Mn.2, or Fe.7, 3, and you can see here there is what you call a spin reorientation transition. These materials show it all. And this spin reorientation transition, I'm showing this is the magnetic field. And around the spin orientation transition, you also find a dielectric anomaly in these materials. So these materials show dielectric anomalies around the magnetic transition, like the spin orientation transition, and also the real temperature. And of course, this temperatures, you see, like the spin orientation transition is very sensitive to magnetic field. If you apply a magnetic field, the orientation transition temperature changes. So we have found magnetodielectric and magnetoelectric or magnetodielectric effect in materials of this kind, where quite large magnetocapacitance in materials when we have two magnetic ions like iron and manganese. Well, then is it ferroelectric? So what we find is ferroelectric polarization is found in materials of this kind, FeMnO3, and this is therefore definitely ferroelectric. Not only that, it is ferroelectric at the real temperature. It is all ferroelectric at the magnetic transition, near the magnetic transition temperature, and I'll quote more evidence. So I would like to remind you what I said, repeat what I said. We did YFeMnO3, I'm sorry, this is something else. So we thought this was because there are two types of magnetic ions with two different types of, anisotropy, this Dielectric interaction, and maybe that is why we are getting this ferroelectricity. So why do we want FeMn? Why not we put FeCr? So we put FeCr, they also show ferroelectricity around the same temperature as the real temperature. And you can see the magnetocapacitance, very large magnetocapacitance at the real temperature. There is a slight dielectric anomaly at the transition. So what I'm showing is, you see, multiferroic and magnetoelectric is not such a great thing anymore. All we need is two magnetic ions in these FeCr, FeMn, any number of combinations you can make. So we have many combinations. I can make large numbers. And of course, right away you say, why do you want yttrium? I can put lutetium, I can put lanthanum, and sure enough, in fact, we did that. Not only the FeCr, which shows this types of polarized ferroelectricity, you can put lutetium. Why not lutetium? That also shows lanthanum will show, and a whole bunch of compounds. And you can put Cr manganese, one only FeMn, CrMn, FeCr. So we have actually generated a very, not infinite number, a very large number of ferroelectrics which are multiferroics. So now I want to rewrite a article now compared to the 10-year-old article, why are there very few multiferroics? My article will be, why are there so many? In fact, that is the, it is all due to magnetically induced ferroelectricity, spin-driven ferroelectricity, which is a very important thing. Of course, we knew that because of TBMNO3, where they had the spiral magnetism, or Mn2O5, where we had a frustrated magnetism giving rise to ferroelectricity. But this is a very general class. I can even predict, I can make compounds why they will be ferroelectric and multiferroic based on this kind of a non-equivalent iron ions. Particularly the ferrite I showed you, aluminum ferrite, is much more interesting to me than these, where you have two different ions. There we do the same ion gives rise to very interesting ferroelectricity, because the two iron ions are different, they show different types of interaction, magnetic interactions, and there is probably breaking of inversion symmetry. So this is the kind of thing, again, some theory has been worked out on this. Recently Chomsky has also collaborated with us a little bit on this. We've just written a paper for this, we have not yet published this, about to be coming. Arising out of that, we are now predicting, we don't have to do all that. There was a paper by Scott from Cambridge and others. He said SMFeO3 PRL a few months ago is ferroelectric, and I think what he says is wrong actually. He said it is because of two iron ions. I don't think so. It is because of samarium, rare earth and iron ions. It is not because of two iron states in that case. So we have now made a general rule. We have made chromides. So again, Sundaresan has done that. Rare earth only with magnetic rare earth ions, like a samarium, as Scott, who did the iron oxide. He did the iron oxide with samarium, and he said it was ferroelectric with the PRL recently. And we have shown a large number of chromides. We didn't do ferrite because ferrites, the magnetic transition temperature is very high, and we can't do measurements at that temperature. So we did chromides where the mean temperatures are low. So a lot of work has been done in our lab by Sundaresan and students, where the mean temperatures are quite low in chromides. We can work on them, and whenever Ln is a magnetic ion, like samarium, gadolinium, or terbium, or whatever, they're all showing multiferroic properties. So we can create a large number of multiferroics by this mechanism as well. This is actually similar to what Scott did, except Scott paper only one ferrite, samarium ferrite, which he obscured to 2 iron ions with 2 non-equivalent iron ions, according to him, which gives rise to it. But the same ferrite doesn't give rise to that if you have a non-magnetic ion in the rare earth side. So it looks like the rare earth is playing an important role. This is a paper where Chomsky has given some explanation in the paper we are just about to write with supervision. So the chromides, the whole family has been done. I'm not showing the data because they will take time to show that. We have got a large number of things of this kind as well. Okay, I will close this talk by showing ferromagnetism and the occurrence of ferromagnetism and ferroelectricity need not be only in these materials but also in nanomaterials. One of the things that has come out of Bangalore from Nehru Center to the work of Sundaresan mainly is that all nanoparticles are ferromagnetic because of the surface. That is very now a universal rule. Doesn't matter which material you take, whether magnesium oxide or aluminum oxide, you don't need a magnetic ion. It will be ferromagnetic because of surface ferromagnetism, because of defects and so on. So you take aluminum oxide, it shows instances where the particle size is small, and if the particle size is big, it immediately becomes diamagnetic. So this has been very well established. Now a lot of people have done this, and for those interested. So what about taking a material like barium titanate? Barium titanate, we make it, you see that a well-known ferroelectric, sure enough that shows magnetic hysteresis. That shows ferromagnetism when the particle size is small. Because if the particle size is large, it is diamagnetic. So does it couple, this surface magnetism of barium titanate, does it couple with the ferroelectricity? In fact, what is interesting, there is some coupling between the surface magnetism of barium titanate and its ferroelectricity. And this has been shown by us some time ago. And not only that, we have also shown materials like cobalt ferrite and barium titanate. We can also make composites of this kind in terms of nanotubes or nanowires or particles. And you can see very nice coupling between the ferroelectric, dielectric, and magnetic properties in this kind of a material. Well, I think there may be a better curve. Yeah, here it is. You can see the magnetocapacitance is very small. You can get 1 or 2% of magnetocapacitance in composites of this kind made in the lab. Well, of course, there is a paper by Ramesh. I never saw the curve was parallel to the x-axis. He said there was 0.1% and what he did, but I couldn't see the change in anything. But it was so small, the figure didn't show it. Well, on a similar material, we have 1.5% of the particles. However, if we make nanotubes or nanowires, we can get up to 5% in composites of 2 nanoparticles, core shell type of nanotube or nanowires of this kind. So barium titanate, cobalt ferrite type of composites, where one is ferroelectric and another is magnetic. Okay, I would like to close this lecture because the time is up. What I want to say is, the whole field where I got interested because of bismuth magnet. That's why I got interested. As a chemist, to me, a lone pair giving rise to ferroelectricity I thought was fantastically interesting at that time. This was some years ago, or 7, 8 years ago. That has taken me to a journey which has given rise to all kinds of things, giving rise to new types of materials, and the mystery of the so-called difficulty we face with multiferroics, generating them is no longer there, according to me. I think it is you can generate multiferroics, magnetoelectrics in large numbers. I don't know what the application will be, which is the best one for what. I'm not going to worry about it. There must be others who will do that. And there's a lot of theory that can still be done, and I hope some theoretical people will collaborate with us, or even otherwise they produce some good theory to explain this kind of dielectric anomalies and ferroelectric anomalies and multiferroid properties for the whole families of oxides that we have shown. Thank you. Okay. Yeah.
Delicate change in the amount of oxygen can produce
that has been that's something, but to bring in non-centrosymmetry, that is another thing. This was why the problem was so difficult. One of the reasons is you get orderings which are much more complex when you have vacancies. And that is what is happening. That gives you a much lower symmetry structure, and therefore also some of it is also being non-succinct in it. If it is a pure stoichiometric crystal, it will be like a perovskite or a simple structure, cubic structure preferably, or something like that. It is not cubic, but still simple enough structure where and so on. So the vacancies or defects help you to get to a low symmetry structure because of the ordering of these things. That's what Paul Midgley's work has shown. Otherwise, we didn't expect it, but when we made carefully these samples, you can never make exactly a sample. But every sample had different stoichiometry, and they had different structure, different properties. And thanks to Paul Midgley's work, definitely these orderings, cation orderings, change. It's very well known in oxides chemistry. This getting high, low symmetry structures because of the defect ordering, and that is happening here also.
So it's a related question. This oxide stoichiometry, it looks like we're going to this bilayer structure in the magnetite.
Bilayer? No. No, it's all simple single. No, it's not bilayer.
So is there a bilayer or multi-layer version?
One can make it. We have not done that. These are all extremely difficult. They are high pressure synthesis. I plan to do it is equivalent to a reduction proper structure, but without doing it, by varying the stoichiometry, I already got one. That's what Paul Midgley has shown. Actually, I got a better structure by varying the oxygen stoichiometry in one of them. Yeah, but actually making it, we'll try. Huh? Yeah, we can do that. We're trying to set up a new high pressure lab in data center this year, and so we can do it right in India one of these days. I'll be able to do that. Yeah.
A lot of the inputs, as I understand it, are multiferroic, but they could give rise to new types of memory devices.
Of course.
Do you have any?
Well, that's what I said in the end. I have not yet looked at that. All this work second half of my talk was all only less than 6 months old. I think we have to now look at what is the best material among these for practical application. Because everything you do, you should get into room temperature. That would be the best. In fact, that is why I changed in gallium ferrite, gallium iron ratio, so that the magnetic transition comes to room temperature. You should have noted it. I've been doing that. So what we have to do is get the dielectric transition also around the room temperature. You have to have a material of that kind for, first of all, good application. And some of them are very good because they have large polarizations. Therefore, if you can get the temperatures, manipulate the temperature right, some of them may have application. I'm going to try to do some of that.
Full variety of material.
You can do Raman number.
But why only one example for ferromagnetic and ferroelectric?
You tell me. I think that's why we all worship God and all that. I don't know. I'm not being religious. I'm just joking. But actually, there's only one ferromagnetic till now. Only one ferromagnet of all the multiferroics, and that is mine, BI-903. And that is why it was so particular that it was not proved to be non-multiferroic. So, no, I don't know why. Ferromagnetism is a difficult thing to happen because in some of these materials, antiferromagnetism is much easier in all these ferrites. Very rarely you get three-dimensional iron oxides which are ferromagnetic. Very rare. Most of them are antiferromagnetic. And so same with chromium, same with manganese. So you don't have a ferromagnetic chromite or ferromagnetic manganite or ferrite. So there is a spinel, that is a ferrimagnet. We are not ferrimagnets. The only aluminum ferrite I did only because it was a ferrimagnet. And I know able to bring it to room temperature, mean temperature. But it is not ferromagnet. It is ferrimagnet. Ferrimagnet, yeah, we can do some. I'm doing that work and don't ask me on that. I know, I have to, Fe3O4 has very interesting polarity. The people have talked about it. All physics literature, you should never ignore that 20, 40, 30-year-old physics papers. I get lots of ideas of it. Like even this GFO3, there was a paper from Bell Lab 35, 40 years ago by Rado and Ramaika, which people have ignored. Suddenly I find they make some of it makes a lot of sense, a lot of measurements, and I'm actually looking at some properties of Fe3O4. See, Fe3O4 is an insulator below the thermal transition. And I will have to look at what the properties are. I have not done that. I plan to.